You are listening to Blueprint for Business, Enterprise Architecture, Design Patterns for Scalable and Resilient Organizations. Subscribe to keep up to date on our latest audiobooks. Blueprint for Business, Enterprise Architecture, Design Patterns for Scalable and Resilient Organizations. Chapter 1, The Architect's Vision, Decoding Enterprise Architecture. Imagine a bustling city. It's not just a random collection of buildings, roads, and power lines. Behind its organized chaos lies an intricate design, a comprehensive plan that dictates where homes go, how water flows, how traffic moves, and how electricity reaches every light switch. This grand design ensures the city functions, grows, and adapts to its inhabitants' needs. Without it, the city would devolve into a confusing, inefficient, and ultimately unlivable sprawl. In many ways, an organization is akin to such a city. It has departments that act like districts, systems that function like utilities, and information that flows like vital rivers. Yet too often, businesses expand and evolve without a coherent, overarching plan. They add new software here, tweak a process there, and integrate a new service somewhere else, often in isolation. The result? Digital sprawl. Inconsistent data, unnecessary complexity, slow innovation. This is where enterprise architecture steps in. 1.1 What is enterprise architecture? Beyond IT diagrams. At its core, enterprise architecture, EA, is the comprehensive blueprint of an organization's mission-critical operations, technology, and information, meticulously designed to achieve strategic goals. It's about more than just drawing diagrams of servers and networks. It's about understanding the entire organizational ecosystem. Its purpose, its people, its processes, and its technology, and ensuring they all work together harmoniously to deliver value. To use our city analogy again, enterprise architecture isn't just about planning the electrical grid, which would be technology architecture. Nor is it only about designing the sewage system, application architecture, or mapping out the demographics of its residents, data architecture. It's about the whole picture. How the city is governed, business architecture, where its resources come from, how its services are delivered, and how it can expand sustainably. It's the master plan that ensures everything connects, communicates, and serves the greater purpose of the city. This distinction is crucial. Many people mistakenly think of architecture, in a business context, as purely an IT function, a technical discipline limited to software or hardware design. While technology is a significant component, enterprise architecture has a far broader scope. It defines the logical structure of an organization's mission and operations, examining how business functions, information flow, applications, and supporting technology interact to deliver on strategic objectives. It's the art and science of aligning an organization's structure and operations with its vision. 1.2 Why does your organization need an architect? The strategic imperative. So, why bother with this grand blueprint? The modern business landscape is dynamic, demanding agility, efficiency, and a clear path through digital transformation. Organizations today face a litany of challenges. Digital transformation gridlock. Many companies get stuck trying to modernize, often because old systems don't communicate or new ones aren't integrated effectively. Technical debt. Accumulated shortcuts and suboptimal past decisions lead to slow, unreliable, and expensive-to-maintain systems. Siloed systems and data. Different departments use different systems that don't talk to each other, leading to inconsistent data, duplicated efforts, and a fragmented view of the customer or business. Slow innovation. The complexity of existing systems makes it difficult and risky to introduce new products, services, or business models. High operational costs. Inefficient processes and redundant technologies inflate expenses and drain resources. Security vulnerabilities. A scattered, unplanned technology landscape presents numerous points of weakness for cyber threats. Consider the hypothetical tale of Global Widgets Inc. For years, Global Widgets ran profitably, albeit with a growing patchwork of systems. Sales had its own CRM, manufacturing had its production planning software, and finance managed its books with a legacy ERP. Each system was robust within its own silo. But when a customer placed an order, sales would key it into their system. then manually email it to manufacturing to input into theirs, and finance would eventually get a paper invoice. When a customer wanted to know their order status, it was a multi-departmental scavenger hunt. If a new product variant was introduced, it had to be configured in 3 different systems, often resulting in errors. Innovation was stifled. Customer satisfaction declined due to delays and inaccuracies. Global Widgets was literally tripping over its own feet. This is precisely where enterprise architecture provides the solution. It offers clarity, a unified understanding of the entire organization. Alignment ensures that every technology investment and process change directly supports business strategy. Agility creates a flexible foundation that can quickly adapt to market changes, new technologies, or shifts in business priorities. Efficiency reduces redundancy, streamlines processes, and optimizes resource allocation. Risk reduction identifies and mitigates technical, security, and operational risks proactively. For Global Widgets, implementing an EA approach meant defining how sales, manufacturing, and finance processes should flow, how customer data should be consistently managed, and which integrated platforms could support this vision. It meant replacing the disconnected patchwork with a cohesive, strategic blueprint, ultimately leading to faster order fulfillment, accurate data, and improved customer experience. 1.3 The 4 domains of EA and how they connect. To create this comprehensive blueprint, enterprise architecture typically organizes an organization's structure and operations into 4 interconnected domains. Business architecture. This is the highest level view, focusing on what the organization does and why. It defines the business strategy, organizational structure, key business capabilities, e.g., customer onboarding, product development, value streams, how value is created and delivered to customers, and the business processes that execute them. It's about understanding the current state and designing the target operating model from a purely business perspective. Data architecture. This domain focuses on the organization's information assets, what information is needed, how it's stored, and how it flows. It defines data strategies, common data definitions, data models, and standards for data quality, storage, and exchange. Its goal is to ensure data is accurate, consistent, accessible, and secure across the enterprise. Application architecture. This layer deals with the organization's applications and systems, which systems execute the business processes, and how they interact. It defines the portfolio of applications, their functions, and their interfaces, ensuring they collectively support the business capabilities. It might define, for example, which CRM system, ERP system, and e-commerce platform are used and how they exchange information. Technology architecture. This is the foundational layer, focusing on the underlying hardware, software, and network infrastructure, the technology platforms that support the applications. It defines the technical standards, infrastructure components, servers, networks, databases, cloud platforms, and environmental requirements needed to operate the applications and store the data. It is critical to understand that these 4 domains are not isolated silos. They are intrinsically linked and interdependent. Business capabilities dictate the information needed and the applications that support them, which in turn rely on specific technology infrastructure. A change in one domain inevitably impacts the others. Enterprise architecture's power lies in managing these interconnections proactively, ensuring that technology investments directly enable business strategy, and data acts as a cohesive force across all operations. 1.4 The journey ahead, what this book will deliver. The task of continuously designing and evolving such a complex enterprise is daunting. How can architects and leaders ensure they are making the right decisions? How can they avoid reinventing the wheel with every new project? This is where enterprise architecture design patterns become invaluable. Just as a master builder has a mental library of proven structural forms, construction techniques, and aesthetic elements, an enterprise architect can leverage a collection of repeatable, proven solutions to common organizational and technological challenges. These patterns are not rigid rules, but templates, guidelines, and best practices that have been shown to work effectively in similar contexts. Over the coming chapters, We will embark on a journey to explore these powerful design patterns. We will delve into categories ranging from strategic business models to robust integration methods, secure IT infrastructures, and resilient data management strategies. You will learn to identify common problems, understand the forces influencing architectural decisions, and discover practical, proven solutions that will empower you to build more scalable, resilient, and adaptive organizations. Whether you are a business leader seeking to understand how technology drives strategy, an IT professional aspiring to a more holistic view, or an architect honing your craft, this book will equip you with a common language, a shared understanding, and a powerful toolkit for designing the future of your enterprise. Let's begin building. Chapter 2, The Power of Patterns, a Foundation for Design. In the previous chapter, we explored enterprise architecture as the grand blueprint for an organization, connecting business strategy with its operational and technological realities. We hinted that this complex task doesn't require constant reinvention. Instead, savvy architects draw upon a powerful concept: design patterns. But what exactly are these patterns, and why are they so fundamental to effective design? 2.1 What is a design pattern? A universal language of solutions. At its most fundamental, a design pattern is a reusable solution to a commonly occurring problem within a given context. It's not a finished, prefabricated component that you simply plug in. Rather, it's a detailed template, a well-defined conceptual framework, or a description of how to solve a particular problem that can be adapted and applied to various situations. Think of it like a master chef's recipe book, not for individual dishes, but for culinary techniques. A sautéing pattern describes a method for cooking food quickly in a hot pan with a small amount of fat. It outlines the problem, how to cook quickly and evenly. The solution: high heat, minimal fat, constant motion. The ingredients: vegetables, meat, and the tools: pan, spatula. The chef then applies this pattern to countless ingredients and dishes, adapting it to mushrooms, chicken, or delicate greens. The core technique remains, but the specific implementation varies. Similarly, in architecture, there are patterns for building strong foundations, for creating efficient ventilation, or for designing light-filled spaces. An arch, for instance, is a structural pattern that has been used for millennia to span openings and support weight. The specific material, size, and decorative elements of an arch might change from a Roman aqueduct to a Gothic cathedral, but the underlying structural principle, the pattern, remains the same. The concept of design patterns gained significant traction in software engineering after the publication of Design Patterns, Elements of Reusable Object-Oriented Software, by the Gang of Four, Erich Gamma, Richard Helm, Ralph Johnson, and John Velasides, in 1994. However, the idea didn't originate there. Architect Christopher Alexander, in his influential 1977 book, A Pattern Language, first articulated the power of patterns as a way to describe good design practices in urban planning and building architecture. He argued that truly great design often repeats successful solutions to recurring problems. 2.2 Why Patterns Matter, Beyond Reinventing the Wheel. The value of design patterns, whether in architecture, cuisine, or enterprise design, cannot be overstated. They offer a multitude of benefits that elevate design from an artisan craft to a more systematic discipline. Efficiency and speed. Instead of starting from scratch to solve every problem, architects can draw upon a proven library of solutions. This dramatically saves time and effort, allowing for faster development and decision-making. It's about building smarter, not harder. Quality and reliability. Patterns represent solutions that have been tested, refined, and validated over time and across many implementations. Using them increases the likelihood of creating robust, stable, and high-quality systems, reducing the risks associated with novel, untested approaches. Communication. Patterns provide a common vocabulary. When architects, developers, and even business stakeholders talk about a layered architecture or an API gateway, they immediately share an understanding of the structure and intent. This reduces ambiguity, improves collaboration, and facilitates knowledge transfer within teams and across the organization. Consistency. By applying known patterns, organizations can foster greater consistency in how their systems are designed and built. This leads to more maintainable systems, easier training for new personnel, and a more coherent overall enterprise landscape. Knowledge transfer and onboarding. For new team members, patterns serve as a didactic tool. They encapsulate expert knowledge and best practices, making it easier for newcomers to understand the rationale behind complex designs and quickly become productive contributors. In essence, patterns allow us to stand on the shoulders of giants, leveraging collective experience and wisdom instead of constantly reinventing solutions to problems that have been solved countless times before. 2.3 Structure of a design pattern, the blueprint format. To be truly useful, a design pattern needs a consistent way of being described. While specific formats can vary, most pattern descriptions adhere to a structure that captures key information. Pattern name, a concise, evocative name that clearly identifies the pattern and enables easy reference and communication, e.g., layered architecture, API gateway. Problem, a description of the recurring problem or set of forces that the pattern is intended to solve. It highlights the context in which the problem typically arises. Solution, the core of the pattern, describing the elements, their relationships, and how they interact to solve the problem. This is typically a conceptual description, not specific code or implementation. Forces considerations, the various technical, economic, or social pressures or trade-offs that influence the design choice and make the pattern applicable or not. For instance, implementing a pattern might reduce complexity in one area but increase it in another. Consequences, the results and implications of applying the pattern. This includes the benefits gained, e.g., improved scalability, tighter security, as well as any potential liabilities, limitations, or trade-offs, e.g., increased latency, higher initial cost. Related patterns, a list of other patterns that typically work well with this one, provide alternatives, or address subproblems related to this pattern. This structured format ensures that a pattern is not just a solution, but a well-understood solution, including its rationale, its context, and its implications. 2.4 Enterprise architecture patterns versus software design patterns. While we've used analogies from software and traditional architecture, it's crucial to distinguish between generic design patterns and enterprise architecture design patterns. They share the underlying philosophy, but differ significantly in their scope and focus. Scope and abstraction level. Software design patterns, like the famous Gang of Four patterns, e.g., singleton, observer, factory method, typically operate at a lower level of abstraction. They define how individual software components, classes, or modules interact within a single application. Enterprise architecture patterns, conversely, operate at a much higher strategic level. They address issues across multiple systems, departments, or even entire organizations. They define how major systems relate, how business capabilities are supported, or how organizational structures influence technology. For instance, the microservices pattern can be applied at the software design level to construct an application, but at the EA level, it refers to a strategic organizational principle, breaking down monolithic business functions into independently deployable units, impacting organizational structure and governance. Stakeholders. Software design patterns are primarily for developers and application architects. EA patterns, however, involve a much broader set of stakeholders. Business leaders, C-suite executives, security officers, compliance teams, and operations personnel are all directly impacted by and contributing to enterprise architectural decisions. Strategic impact and lifespan. Decisions made using EA patterns have profound, long-lasting strategic implications for the entire organization. They can dictate how quickly a company can introduce new products, adapt to market shifts, or enter new markets. A misplaced software design pattern might lead to a refactor of a single application. A poorly chosen EA pattern could cripple an entire organization's agility for years. Context and domain. EA patterns often incorporate business domain knowledge, organizational culture, and regulatory constraints, alongside technical considerations. They are not merely technical constructs, but socio-technical patterns that consider the interplay between people, processes, and technology in an organizational context. Consider the service-oriented architecture, SOA, pattern. At a pure software level, it's about exposing reusable code components. But as an EA pattern, it's about identifying common business services, like verify customer account or process payment, and making them available across the entire enterprise, allowing different applications and departments to consume them consistently, thereby fostering business agility and reducing redundancy. This decision has implications far beyond a single development team. In the next chapters, we will dive deep into specific enterprise architecture patterns across various domains: strategic, integration, data, and security, demonstrating how these foundational blueprints empower organizations to build sustainable success. These are the tools that allow organizations to move beyond mere patchwork solutions and instead engineer robust, adaptable, and future-ready enterprises. Chapter 3: Strategic Blueprints. Core Enterprise Architecture Patterns. In our exploration of enterprise architecture, we've established that its purpose is to create a cohesive blueprint for an organization, aligning business strategy with its technology and operations. We also learned that design patterns offer reusable solutions to common problems, elevating design from an ad hoc process to a structured discipline. Now, it's time to delve into the foundational EA patterns, the strategic blueprints that define the overall structure and interaction principles of an enterprise's systems. These patterns are critical because they lay the groundwork for how effectively an organization can scale, adapt, and innovate. 3.1 Layered Architecture. Organizing the enterprise stack. Imagine a multi-story commercial building. Each floor has a distinct purpose. The ground floor is public-facing retail, the next few floors house administrative offices, and the top floors might contain specialized data centers or equipment. Access to each floor is controlled, and while services like electricity and plumbing run through the entire building, the functions of one floor are generally independent of another. This architectural principle is analogous to layered architecture in the enterprise. Problem: without a clear structure, IT systems can become a tangled mess, a spaghetti architecture where every component can directly call any other component. This leads to high coupling, making systems difficult to understand, maintain, test, and evolve. A change in one part of the system might inadvertently break something seemingly unrelated elsewhere. Solution: layered architecture divides a system into distinct horizontal layers, each performing a specific, well-defined set of functions. Each layer typically communicates only with the layers immediately above and below it, enforcing a separation of concerns. Common layers in an enterprise context include presentation layer, e.g., user interfaces, web portals, mobile apps, responsible for displaying information to users and handling user input. Business logic service layer, e.g., core business processes, application services, contains the heart of the business rules and operations. This layer acts as an intermediary, orchestrating processes and coordinating data flow. Data access layer, e.g., repositories, DAOs, handles communication with data sources, abstracting the details of how data is stored and retrieved. Data layer, e.g., databases, data warehouses, the actual persistent storage mechanisms. Benefits: modularity. Clearly defined boundaries make components within each layer easier to develop, test, and maintain independently. Separation of concerns. Each layer focuses on a specific aspect, reducing complexity and cognitive load. Flexibility. Technologies within a layer can be changed or upgraded without significantly impacting other layers. E.g., changing the database in the data layer doesn't affect the user interface directly. Scalability allows for independent scaling of different layers if particular functions become bottlenecks. Trade-offs can introduce performance overhead due to multiple communication hops between layers and may not be suitable for highly dynamic or single-function applications where a simpler architecture might suffice. Layered architecture is a foundational pattern that brings order to potential chaos, making large and complex systems more manageable and resilient. 3.2 Service-oriented architecture, SOA. Services as building blocks. building upon the idea of modularity service-oriented architecture, SOA, focuses on creating reusable, platform-agnostic business services that applications can consume. Problem: in many organizations, similar functionalities are duplicated across different applications. For example, a customer lookup function might be independently built into the CRM system, the billing system, and the customer support portal. This leads to inconsistent data, maintenance nightmares. Fixing a bug means fixing it in multiple places, and slow development cycles. Solution: SOA defines a way to make discrete business functionalities available as services over a network. These services are loosely coupled, meaning they operate independently, and are accessed via standardized interfaces, often using XML-based protocols like SOAP or, more recently, REST-TFL APIs. Any application or system that needs a particular function can simply call the relevant service, rather than re-implementing it. An Enterprise Service Bus, ESB, which we'll discuss more in Chapter 4, is often used to facilitate communication and mediation between these services. Benefits: reusability. Services can be reused across the enterprise, significantly reducing development time and cost. Flexibility and agility. New applications can be composed quickly by orchestrating existing services. Changes to a service can be made independently without affecting its consumers, as long as the interface remains stable. Interoperability. Services can be built using different technologies but still communicate, breaking down technological silos. Business alignment. Services are often defined based on business capabilities, making the architecture directly align with strategic business functions. Example: imagine an order fulfillment service. It comprises all the logic needed to process an order, check inventory, initiate shipping, and update customer status. This service can be consumed by the organization's e-commerce website, its internal sales system, or even by a partner's order entry system. Each consumer simply sends an order request to the service and receives a response without needing to know the internal workings of the fulfillment process. SOA laid crucial groundwork for subsequent architectural advancements by emphasizing loose coupling and reusability at a service level. 3.3 Event-Driven Architecture, EDA, responding to chain. While SOA is excellent for explicit requests and responses, many business processes involve reacting to occurrences. This is where event-driven architecture, EDA, excels. Problem: many systems operate in isolation, requiring direct calls to update each other. This creates tight coupling, slows down processing, and makes systems brittle. For example, when a new customer signs up, the CRM needs to be updated, a welcome email needs to be sent, and the marketing system needs to be notified. A direct, sequential call to each system can be slow and fail if one system is down. Solution: EDA is an architectural style centered around the production, detection, consumption of, and reaction to events. An event is a significant change in state, e.g., customer signed up, order placed, inventory low. When an event occurs, it is published to an event broker, like a message queue or streaming platform, and interested subscribers, other systems or services, can react to it independently and asynchronously. Benefits: decoupling. Senders, event producers, and receivers, event consumers, are largely unaware of each other, making the system highly flexible and resilient. Scalability. Events can be processed in parallel, allowing for high throughput and responsiveness, especially under heavy load. Responsiveness. Systems can react to real-time changes, enabling immediate business actions. Fault tolerance. If a subscriber goes down, events can queue up and be processed when it recovers, without affecting the producer. Analogy: think of a newspaper publishing system. Reporters, producers, write articles, events, and send them to the newspaper event broker. Readers, subscribers, who are interested in specific topics, e.g., sports, politics, pick up the newspaper and read the relevant articles. The reporters don't know who reads their articles, and the readers don't need to know the reporters directly. Case study idea: an e-commerce platform uses EDA. When a product ordered event occurs, it triggers multiple independent actions. The inventory service updates stock levels. The payment service initiates billing. The shipping service prepares the shipment. The customer notification service sends an order confirmation email. The analytics service records the sale. All these actions happen concurrently and asynchronously, making the system robust and highly responsive. EDA is crucial for building reactive systems that can respond dynamically to an unpredictable flow of information. 3.4 Microservices architecture as an EA principle. Breaking down monoliths. Building on the principles of SOA, microservices architecture has emerged as a predominant pattern for developing and deploying modern applications, specifically championed as a strategic EA choice. Problem: large, monolithic applications, while simpler to build initially, become increasingly difficult to manage as they grow. They are slow to develop, challenging to deploy. A small change requires redeploying the entire application. Hard to scale, you have to scale the whole thing even if only one part is strained, and restrict technology choices. Everyone must use the same language and framework. This phenomenon is often termed the monolith dilemma. Solution: microservices architecture strategically decomposes a large application into a collection of small, independently deployable, loosely coupled services. Each service embodies a specific business capability, runs in its own process, and communicates with others via lightweight mechanisms, like REST APIs or event streams. Critically, each microservice usually owns its own data store and can be developed, deployed, and scaled independently by small, autonomous teams. Benefits: increased agility. Smaller codebases are easier for teams to manage, allowing for faster development and continuous delivery. Independent deployment. Services can be deployed independently, reducing the risk of downtime and accelerating release cycles. Technology diversity. Teams can choose the best technology stack for each service, leveraging polyglot persistence and programming languages. Component scalability. Individual services that require more resources can be scaled up or down independently, optimizing infrastructure costs. Team autonomy aligns well with small, cross-functional teams, fostering greater ownership and faster decision-making. This relates to Conway's Law, which we will discuss in Chapter 9. Context as an EA choice. Deciding to adopt microservices is a significant enterprise architecture decision. It's not just a technical pattern. It deeply impacts organizational structure, operational practices, and cultural norms. It requires careful consideration of how services interact, how data consistency is managed, and how governance is applied in a highly distributed environment. For example, a large financial services company might decompose its monolithic lending application into microservices for loan origination, credit scoring, collateral management, and disbursement, each handled by dedicated teams. These strategic blueprints, layered architecture for structure, SOA for service reuse, EDA for reactive systems, and microservices for highly modular and agile development, form the bedrock of a well-designed enterprise. They provide the fundamental guiding principles for organizing and evolving complex systems, allowing organizations to navigate the complexities of the digital age with greater confidence and adaptability. In the next chapter, we'll turn our attention to the critical patterns that enable these systems to talk to each other. Integration. Chapter 4. The Integration Imperative. Connecting disparate systems. In the previous chapter, we explored some core strategic EA patterns that define how an enterprise structures its internal systems. However, few organizations operate with a single, perfectly unified system. The reality is often a heterogeneous mix. Legacy mainframes, modern cloud applications, SaaS solutions, partner systems, and various bespoke databases. Getting these disparate systems to communicate effectively is not just a technical challenge. It's a business imperative. Without seamless information flow, processes break down, data becomes unreliable, and competitive advantage is lost. This is the realm of integration patterns. 4.1 The Integration Challenge. Bridging silos. Imagine a construction site where different teams, using different languages and different building codes, are trying to build parts of the same structure. That's the essence of the integration challenge in many organizations. Information exists in silos, often in formats incompatible with other systems. Problem: Businesses rely on a multitude of applications and data sources, e.g., CRM, ERP, accounting software, marketing platforms, supply chain management systems. When these systems don't share information effectively or consistently, it leads to data inconsistencies. The same customer might have different addresses in the sales system and the billing system. Manual data entry and duplication. Employees waste time copying data from one system to another, introducing errors. Slow processes, information bottlenecks delay critical business operations. Limited insights. A complete, unified view of customers, products, or operations is impossible. Vendor lock-in, swapping out one component is difficult due to deep, brittle integrations. Importance. Seamless data flow and process orchestration are critical for modern business. Whether it's fulfilling an order, onboarding a customer, or analyzing market trends, the efficiency and accuracy of these processes fundamentally depend on how well systems can communicate and exchange information. Fortunately, enterprise architecture offers proven integration patterns to address these complexities. 4.2 Message Bus/Enterprise Service Bus, ESB. Centralized messaging. One of the earliest and most influential integration patterns, the message bus, often exemplified by an enterprise service bus, ESB, provides a centralized communication backbone. Problem. When every application needs to connect directly to every other application it communicates with, the number of connections grows exponentially, n*(n1/2). This point-to-point integration leads to a complex, fragile, and unmanageable web of connections, often termed spaghetti integration. Adding a new application requires modifying many existing connections. Solution. An ESB acts as a specialized intermediary or middleware layer. Instead of applications connecting directly, they communicate with the ESB. The ESB is responsible for routing, directing messages from a source application to the correct destination application. Transformation, converting data formats or protocols between disparate systems, e.g., XML to JSON, or a legacy mainframe format to a modern API call. Mediation, handling communication protocols, security, and message enrichment. Orchestration, chaining together multiple service calls to complete a complex business process. Benefits, centralized control. All integrations are managed in one place, providing a single point of visibility and control. Decoupling, applications are loosely coupled from each other. They only need to know how to communicate with the ESB. This makes it easier to add, modify, or replace applications without affecting others. Standardization enforces consistent communication patterns and data formats across the enterprise. Scalability. The ESB can handle high volumes of messages and often provides capabilities for load balancing and fault tolerance. Analogy. Think of an airport control tower managing all air traffic. Instead of planes flying directly between every two cities, they communicate with the control tower, which then guides them to their destinations, managing different plane types, runway availability, and weather conditions. Trade-offs. ESBs can become monolithic bottlenecks themselves if not managed properly. They require a dedicated team to develop and maintain, and they can stifle agility if every small integration requires the ESB team's intervention. Modern approaches often favor more decentralized integration patterns, but ESBs remain a powerful solution for complex, enterprise-level integration needs. 4.3 API Gateway, the front door to your services. In the era of microservices and mobile applications, the API gateway has become an indispensable integration pattern, especially for exposing services externally. Problem. As organizations embrace microservices, they end up with numerous small services, each potentially with its own independent API. Managing authentication, rate limiting, logging, and routing for dozens or hundreds of individual services becomes a significant challenge, especially for client applications, like mobile apps or external partners, that might need to interact with multiple services to fulfill a single request. Solution: an API gateway acts as a single entry point for all client requests. Instead of directly calling individual backend services, clients interact with the API gateway. The gateway then routes the requests to the appropriate backend services, aggregates responses, and can perform common cross-cutting concerns such as authentication and authorization, verifying client identity and permissions, rate limiting and throttling, preventing abuse or overload, traffic management, routing requests, load balancing, caching, storing frequently accessed data to reduce backend load, monitoring and logging, centralized collection of API usage data, protocol translation, converting client protocols to backend protocols if necessary. Benefits: simplified client experience. Clients only need to know one URL and one set of authentication credentials to access multiple backend services. Enhanced security. Centralizes security controls and shields backend services from direct exposure. Improved performance. Can optimize network calls, e.g., by aggregating multiple microservice calls into one API call for a client. Abstraction. Decouples clients from the specific backend service implementations, allowing backend services to evolve independently without breaking client applications. Example: a popular mobile banking app uses an API gateway. When a user requests their account balance and recent transactions, the API gateway receives this single request, then internally calls the account service for the balance and the transaction history service for transactions, aggregates the data, and sends a single, unified response back to the mobile app. The API gateway is often used in conjunction with microservices architectures to manage their complexity and provide a clean external interface. 4.4 Publish-Subscribe Pattern, Decoupled Communication. The Publish-Subscribe (PubSub) pattern is a powerful mechanism for achieving high levels of decoupling and scalability in event-driven architectures. Problem: systems often need to react to events occurring in other systems, but they shouldn't be tightly coupled. For example, when a customer updates their address in the CRM, the logistics system, billing system, and marketing system all might need to know, but the CRM shouldn't have to know about or directly call each of them. Solution: in a PubSub system, publishers send messages events to abstract categories called topics or channels. Subscribers express interest in specific topics and receive all messages published to those topics. The key innovation is that publishers and subscribers have no direct knowledge of each other. Messages are typically routed through an intermediary, like a message broker, e.g., Apache Kafka, RabbitMQ, AWS SNS SQS. Benefits: extreme decoupling. Publishers and subscribers are completely independent. This allows for high flexibility and scalability. New subscribers can be added without modifying publishers, and vice versa. Asynchronous communication. Messages are sent and processed asynchronously, improving responsiveness and fault tolerance. If a subscriber is temporarily down, messages can queue up and be processed when it recovers. Scalability. Allows for massive fan-out, where one event can trigger actions in many different systems without overwhelming the publisher. Analogy: consider a public announcement system at a train station. The announcer publisher broadcasts announcements about train arrivals, departures, messages to specific platform numbers, topics. Travelers waiting at those platforms, subscribers, hear the announcements relevant to their train. The announcer doesn't know who is listening, and the travelers don't need to know the announcer directly. Case study idea: a manufacturing plant uses a pub subsystem. When a machine completes a production batch, it publishes a batch completed event to a production events topic. The inventory management system subscribes to this topic to update finished goods stock. The quality control system subscribes to trigger an inspection for that batch. The maintenance system subscribes to log machine uptime. All these systems react independently to the single event, making the plant's operations highly automated and responsive. 4.5 Data synchronization patterns, e.g., batch sync, event-driven sync. Beyond simple message exchange, a common integration challenge is ensuring data consistency and currency across multiple systems that inherently hold copies of the same or related data. Problem: critical business data, such as customer information or product catalogs, often resides in various operational systems. Keeping these copies consistent and up-to-date across all systems is crucial for operational integrity and accurate reporting. Challenges include differing schemas, data volumes, and acceptable latency. Solution: various patterns exist depending on the requirements for freshness and complexity. Batch synchronization: data is collected, transformed, and exchanged between systems in large batches at predetermined intervals, e.g., nightly, hourly. This is suitable when real-time updates are not critical. Example: a marketing system might pull customer demographic data from the CRM system nightly to update its segmentation lists. Event-driven synchronization leverages the pub-sub pattern or other messaging mechanisms to propagate changes in data almost immediately. When a record is updated in a source system, an event representing that change is published, and interested destination systems consume the event to update their copies. Example: when a customer updates their address in the customer portal, an event is published, triggering immediate updates in the billing system, shipping system, and loyalty program. Request reply, API-driven. One system requests data from another system in real time via an API call when it needs the most current information. This is often used for read-only access to master data. Example: an e-commerce site might call a product catalog API to fetch the latest price and inventory before displaying an item to a customer. Trade-offs: each pattern involves trade-offs between data freshness, latency, complexity of implementation, and resource consumption. Batch sync is simpler, but less real-time. Event-driven sync offers high freshness, but requires robust messaging infrastructure and careful handling of eventual consistency. Request reply provides real-time data, but can increase network traffic and introduce points of failure. Effective integration is the circulatory system of the modern enterprise. By carefully choosing and applying these integration patterns, organizations can connect their disparate systems, unblock information flow, and build a more responsive, efficient, and interconnected digital ecosystem. In the next chapter, we will shift our focus to the crucial patterns for managing and leveraging the lifeblood of the enterprise, its data. Chapter 5: Data as the New Oil. Data architecture patterns. In today's digital economy, data has emerged as one of an organization's most valuable assets. It's the raw material for insights, the fuel for artificial intelligence, and the foundation for informed decision-making. However, much like crude oil, raw data often needs extensive refinement, distribution, and strategic management to unlock its true value. Without proper data architecture, organizations can drown in a sea of information, struggling with inconsistency, poor quality, and an inability to extract meaningful intelligence. This chapter explores key data architecture patterns that help organizations effectively manage, store, and leverage their data. 5.1: The Data Landscape. From siloed to strategic asset. The journey of data within an enterprise is complex and ever-evolving. Historically, data lived in isolated application databases, each serving a specific departmental function. As business needs grew more interconnected, the limitations of this siloed approach became painfully apparent. Problem: organizations today face an explosion of data, arriving from diverse sources, IoT devices, customer interactions, social media, internal systems, in myriad formats: structured, semi-structured, unstructured. Common struggles include disparate formats and locations, data scattered across numerous databases, cloud services, and legacy systems, making it hard to get a unified view. Poor data quality. Inaccurate, incomplete, or inconsistent data leading to flawed decisions. Compliance and governance challenges. Difficulty tracking data lineage, ensuring privacy, e.g., GDPR, CCPA, and meeting regulatory requirements. Lack of actionable insights. Inability to effectively analyze vast datasets to identify trends, predict outcomes, or optimize operations. Importance. Data, when properly managed and analyzed, is foundational for a myriad of strategic initiatives. From personalized customer experiences and efficient supply chains to groundbreaking product development and effective risk management. Treating data as a strategic asset, rather than merely a byproduct of operations, is paramount for competitive advantage. Effective data architecture patterns provide the blueprints for transforming raw data into actionable intelligence. 5.2 Data Warehouse, the Analytic Hub. One of the most enduring and widely adopted data architecture patterns for analytical purposes is the data warehouse. Problem: operational databases, those that support day-to-day transactions like order processing or customer interactions, are optimized for fast reads and writes of individual records. They are not designed for complex analytical queries that might involve scanning millions of historical records or joining data across many tables from different source systems. Running such queries directly on operational systems would severely impact their performance and availability. Solution: a data warehouse is a subject-oriented, integrated, time-variant, and non-volatile collection of data used to support management's decision-making process. Subject-oriented organizes data around major business subjects, e.g., customers, products, sales, rather than operational applications. Integrated data is extracted from various operational sources, cleaned, transformed, and loaded into a consistent format, resolving inconsistencies and standardizing definitions. Time-variant data is historical, capturing changes over time, allowing for trend analysis and historical comparisons. Non-volatile: once data is in the warehouse, it generally remains stable and is not updated or deleted, providing a stable basis for analysis. Benefits: consistent historical view provides a single, clean, and consistent source of historical data for reporting, analysis, and business intelligence. Improved decision support enables complex analytical queries without impacting operational systems. Better data quality: data undergo cleansing and transformation during the loading process, improving overall quality. Scalability for analytics, optimized for read-heavy analytical workloads. Analogy: if operational databases are like individual cash registers recording transactions, a data warehouse is like a meticulously organized library dedicated to preserving and cross-referencing all historical sales records for research and strategic planning. Analysts come to the library to study trends over decades, not to process a single purchase. While traditional data warehouses primarily handle structured, relational data, the concept has evolved with cloud-native data warehouses like Snowflake or Google BigQuery that offer immense scalability and flexibility, blurring the lines with data lakes. 5.3 Data Lake, storing everything, unstructured and structured. The rise of big data and the need to store vast quantities of diverse data, irrespective of its immediate analytical purpose, led to the emergence of the data lake. Problem: traditional data warehouses require data to be structured and transformed before it's loaded. This schema-on-write approach makes it difficult and time-consuming to incorporate new, rapidly changing, or unstructured data sources, like social media feeds, IoT sensor data, emails, videos. Furthermore, transforming data can be expensive and requires knowing exactly how the data will be used in advance. Solution: a data lake is a centralized repository that allows you to store all your data, regardless of format, structured, semi-structured, unstructured, at any scale. It uses a schema-on-read approach, meaning data is stored in its raw format, and a schema is applied only when the data is accessed for analysis. This is why data lakes are often described as schemaless or schema-agile. Benefits: flexibility, can store any type of data, making it ideal for exploratory analytics, machine learning, and future use cases that are not yet defined. Scalability, designed to handle petabytes and exabytes of data economically, especially with cloud storage solutions. Cost-effective storage, raw data is typically stored on inexpensive object storage, e.g., Amazon S3, Azure Blob Storage. Supports advanced analytics. The ability to store raw, diverse data makes data lakes perfect for data scientists and machine learning engineers who need access to all available information. Analogy: if a data warehouse is a structured, purified reservoir of water, a data lake is a vast, natural lake that collects precipitation from all sources, streams, rain, rivers, in its natural form. You can swim in it, fish in it, or, with specialized tools, extract specific samples for scientific analysis. Trade-offs: Data lakes can become data swamps without proper governance, metadata management, and discoverability tools. It's crucial to have a strategy for organizing and cataloging the data to prevent it from becoming unusable. Organizations often employ both a data lake for raw, diverse data and a data warehouse for curated, structured analytical data, allowing them to leverage the strengths of each. 5.4 Master Data Management, MDM, a single source of truth. To combat data inconsistencies and duplication, especially for critical business entities, Master Data Management, MDM, provides a solution. Problem. In a typical organization, vital master data, referring to core business entities like customers, products, employees, or locations, is often duplicated, fragmented, and inconsistent across various operational systems. For example, a customer's address might be slightly different in the sales CRM versus the billing system. This leads to errors, poor customer service, inaccurate reporting, and compliance risks. Solution. MDM is not a single technology, but a discipline, a set of processes, and a pattern of technologies aimed at creating a consistent, accurate, and authoritative golden record for core business entities. MDM solutions typically involve data aggregation, collecting master data from multiple source systems, data harmonization, cleansing, deduplicating, and standardizing the data governance, establishing clear ownership, policies, and processes for data creation and maintenance, data distribution, publishing the golden record back to consuming systems or making it available via APIs. Benefits. Improved data quality, ensures accuracy, completeness, and consistency of critical business data. Reduced errors and duplication, eliminates manual reconciliation efforts and associated mistakes. Enhanced customer experience, provides a unified view of the customer across all touchpoints. Better decision-making, builds trust in data used for reporting, analytics, and strategic planning. Regulatory compliance, helps meet compliance requirements for data privacy and integrity. Case study idea. A large retailer has separate systems for online sales, in-store point of sale, and loyalty programs. Before MDM, a customer might have multiple entries, making it impossible to see their complete purchase history or preferences. Implementing an MDM solution creates a single, definitive customer golden record that syncs across all systems, enabling personalized offers and a seamless omnichannel experience. MDM patterns often include approaches like registry style, merely linking master data across systems, consolidation style, creating a golden record but not enforcing its use everywhere, and coexistence style, maintaining separate unique IDs in systems but synchronizing common data, each with varying levels of integration and data authority. 5.5 Data Mesh, decentralized data ownership. As organizations grow and data becomes even more central, traditional centralized data teams and platforms can become bottlenecks. The data mesh is a more recent and transformative data architecture pattern that decentralizes data ownership. Problem. Centralized data teams struggle to keep up with the diverse and rapidly evolving data needs of a large, distributed enterprise. Data platforms often become monolithic, trying to serve too many purposes, leading to friction, slow delivery, and a lack of accountability for data quality at the source. Solution. The data mesh pattern is built on 4 core principles. Domain-oriented ownership. Data is owned and managed by the operational domain teams that produce it, e.g., the sales team owns customer data generated by their CRM. Data is treated as a first-class product of these domains. Data as a product. Data domains are responsible for producing high-quality, consumable, and trustworthy data products, e.g., a customer 360 data product that meet the needs of their consumers. Self-serve data platform. A centralized platform team provides automated tools and infrastructure, enabling domain teams to easily create, publish, and consume data products without manual intervention. Federated computational governance. A decentralized decision-making body establishes global policies, e.g., security, compliance, interoperability standards, that are then implemented and enforced locally by domain teams through the self-serve platform. Benefits. Scalability. distributes data ownership and processing, allowing the enterprise data ecosystem to scale with organizational growth. Agility and faster delivery. Domain teams can innovate on their data products quickly without waiting on a central team. Domain expertise. Data quality and context are better maintained because the people closest to the source data are responsible for it. Improved data quality and trust. Treating data as a product encourages domain teams to deliver reliable and well-documented data. Trade-offs. Implementing a data mesh requires significant organizational and cultural shifts, strong engineering capabilities for the self-serve platform, and careful governance to ensure global interoperability and compliance. The patterns in this chapter represent different strategic approaches to managing an organization's most valuable resource. From providing structured analytics, data warehouse, to enabling raw data exploration, data lake, ensuring data consistency, MDM, and fundamentally rethinking data ownership, data mesh. These patterns are essential for any enterprise seeking to harness the power of its information assets. Next, we will explore how to protect these valuable assets by focusing on critical security architecture patterns. Chapter 6: Securing the Fortress. Security architecture patterns. In an increasingly interconnected digital world, the notion of a secure enterprise is not just about keeping intruders out. It's about building a robust, resilient system that protects valuable assets, maintains operational continuity, and ensures compliance with ever-evolving regulations. Cybersecurity threats are no longer isolated incidents, but sophisticated, persistent challenges that can cripple businesses, erode customer trust, and lead to significant financial and reputational damage. Therefore, security cannot be an afterthought. It must be designed into the very fabric of the enterprise architecture from the ground up. This chapter explores essential security architecture patterns that help organizations build defensive layers and proactively manage risk. 6.1: The ever-evolving security landscape, no longer an afterthought. Historically, security was often bolted on as a perimeter defense, building a strong firewall and hoping for the best. This approach is no longer sufficient. Problem: the digital attack surface has expanded exponentially. Cloud computing, mobile devices, remote workforces, IoT, and complex supply chain integrations have shattered traditional network perimeters. Attackers are more sophisticated, employing varied tactics from phishing and ransomware to supply chain attacks and sophisticated persistent threats. Meanwhile, regulatory demands like GDPR, HIPAA, PCI DSS for data privacy and security are becoming stricter and more punitive. Importance: a robust security architecture is paramount for several reasons. Data protection, safeguarding sensitive customer data, intellectual property, and financial information. Business continuity, preventing disruptions caused by cyberattacks, ensuring systems remain operational. Trust and reputation, maintaining customer and stakeholder confidence. Regulatory compliance, avoiding legal penalties and fines. Risk management, proactively identifying, assessing, and mitigating security risks across the enterprise. Effective security architecture patterns provide structured, repeatable solutions to address these challenges, ensuring that security is an inherent quality of the system, not an optional add-on. 6.2: Identity and Access Management, IAM, knowing who's who. The first line of defense in any system is controlling who can access what. Identity and Access Management, IAM, is the foundational security pattern for this crucial task. Problem: in a large organization, employees, contractors, partners, and customers need access to a multitude of applications and data sources. Managing individual user accounts and assigning specific permissions for each system manually is prone to errors, incredibly time-consuming, and creates numerous security vulnerabilities, e.g., forgotten to revoke access for departed employees. Solution: IAM centralizes the management of digital identities and the control of access privileges across an organization's resources. It encompasses several key sub-patterns and functionalities. Centralized Identity Store, a single, authoritative directory of users, e.g., Active Directory, LDAP, cloud identity providers. Authentication, verifying a user's identity, e.g., username password, multi-factor authentication, MFA, biometrics. Patterns like single sign-on, SSO, allow users to log in once and gain access to multiple independent applications without re-authenticating, improving user experience and security. Authorization, determining what an authenticated user is permitted to do. Role-based access control, RBAC, is a common pattern where permissions are assigned to roles, e.g., sales manager, and users are assigned to roles, simplifying management. More granular attribute-based access control, ABAC, uses various attributes, user characteristics, resource properties, environmental conditions for dynamic access decisions. User provisioning, deprovisioning, automating the creation and deletion of user accounts and their entitlements across systems. Benefits, enhanced security, reduces the risk of unauthorized access through strong authentication and granular authorization. Reduced administrative overhead, automates user lifecycle management, saving time and resources. Improved user experience, SSO streamlines access for legitimate users. Compliance, provides audit trails and enforces policies necessary for regulatory compliance. Analogy, think of IAM as the security checkpoint at an airport. It verifies your identity, authentication, checks your boarding pass to see where you are allowed to go, authorization, and keeps a record of your entry, auditing. SSO is like having one pass that gets you through multiple gates without showing it repeatedly. 6.3 Security Zones/network segmentation, dividing your digital castle walls. Even with strong IAM, systems can experience breaches. The security zones or network segmentation pattern aims to limit the damage from a breach by compartmentalizing the network. Problem: a flat network, where all systems reside on the same broadcast domain, means that once an attacker breaches one system, they have unfettered access to move laterally throughout the entire network. This makes containing an attack incredibly difficult. Solution: network segmentation involves dividing a larger network into smaller, isolated, logically separate zones. Each zone has a defined trust level and strict controls, e.g., firewalls, access control lists, governing traffic entering or leaving it. Common security zones include DMZ, demilitarized zone, often houses public-facing servers, web servers, email servers that need to be accessible from the internet but are isolated from the internal corporate network. Internal network contains sensitive internal systems, e.g., databases, internal applications that are not directly exposed to the internet. Production versus development test, separating environments to prevent development issues from impacting production and to contain potential compromises. User segments, separating corporate users from guest Wi-Fi or department-specific networks. Benefits, limits breach impact. If one zone is compromised, the spread of the attack is contained, protecting other parts of the network. Enhances control, allows for granular security policies to be applied to different categories of assets. Simplifies policy enforcement, easier to audit and enforce security rules for smaller, well-defined segments. Case study idea. A financial institution separates its customer-facing web servers in a DMZ, its internal application servers in a separate network segment, and its highly sensitive database servers in the most restricted internal segment. Firewalls are configured to allow only specific, necessary traffic flows between these zones, preventing a compromise of the web server from directly exposing the database. This pattern is a crucial aspect of defense in depth, assuming that perimeter defenses can always be bypassed and therefore building internal barriers. 6.4 Principle of least privilege, just enough access. A fundamental maxim in security design is the principle of least privilege, POLP. Problem: granting users, applications, or services more permissions than they actually need to perform their legitimate functions creates an unnecessary attack surface. If an account with excessive privileges is compromised, the damage inflicted can be far greater than if it only had the bare minimum access. Solution: according to POLP, every user, program, or process should be granted only the minimum necessary permissions to perform its intended task, and no more. This means no unnecessary admin rights, Users should not have administrator privileges on their workstations unless absolutely required for their job function. Granular permissions. Applications should only have access to specific databases, files, or network resources they absolutely need, rather than broad all-access permissions. Temporary permissions. For sensitive operations, highly privileged access should be granted only for a limited period, through just-in-time access management. Benefits. Reduces attack surface. Limits the potential damage an attacker can do if they compromise a user account or system. Improves containment. Constrains lateral movement within a network by an attacker. Enhances auditability. Makes it clearer to track who did what with which permissions. Analogy. Consider a janitor in an office building. Under the principle of least privilege, they would be given keys only to the areas they need to clean their assigned floors, supply closets, not the keys to the executive offices, the server rooms, or the company vault. They have just enough access to do their job, but no more. 6.50 Trust architecture. Never trust, always verify. Building on the evolution of perimeter-based security and the principle of least privilege, Zero Trust architecture, ZTA, represents a paradigm shift in how security is approached. Problem: traditional security models implicitly trust anything inside the network perimeter. However, with cloud adoption, highly distributed workforces, and sophisticated internal threats, the concept of a trusted inside and untrusted outside is obsolete. Solution: Zero Trust operates on the principle of never trust, always verify. It dictates that no user, device, or application, whether inside or outside the network, should be implicitly trusted. Every single access attempt, regardless of its origin, must be continuously authenticated, authorized, and validated with the strictest possible security controls before access is granted. Key tenets include: verify explicitly. All access is continually authenticated and authorized based on all available data points, including user identity, device health, location, service, and data classification. Use least privilege access, granting just-in-time and just enough access, dynamically adjusting permissions for each request. Assume breach. Design systems with the assumption that breaches will occur and focus on limiting their blast radius and containing them quickly. Microsegmentation. Break networks into tiny, isolated segments and enforce policy for every microsegment. Benefits: superior security posture. Significantly reduces the risk of lateral movement once a compromise occurs. Adaptable to distributed environments. Ideal for cloud, hybrid, and remote work scenarios where traditional perimeters are non-existent. Improved compliance. Facilitates stricter enforcement of security policies. Zero Trust is not a single product, but a philosophy and a set of architectural principles that guide how security is interwoven throughout the entire enterprise. It represents a mature approach to cybersecurity, recognizing the inherent vulnerabilities of modern IT landscapes. These security architecture patterns are foundational for building resilient organizations in an era of constant threat. They demonstrate that security is not a separate project, but an integral part of enterprise architecture, requiring strategic foresight and continuous vigilance. In the next chapter, we will explore patterns related to governance and compliance, ensuring that the enterprise operates effectively within structured boundaries and regulatory requirements. Chapter 7: Governance and Compliance. Establishing order. A robust enterprise architecture, like a well-designed city, requires more than just strategic blueprints, integrated systems, and fortified defenses. It also needs effective governance, a framework of rules, processes, and decision-making bodies that ensure coherence, alignment, and controlled evolution. Without proper governance, even the best technical patterns can devolve into chaos, leading to inconsistent standards, duplicated efforts, and an inability to meet regulatory and business demands. This chapter explores patterns that help organizations establish order, align their IT efforts with business strategy, and ensure adherence to internal policies and external regulations. 7.1 The Need for Order. Balancing agility with control. In today's fast-paced business environment, organizations constantly strive for agility, the ability to respond quickly to change. However, unchecked agility can lead to fragmentation, technical debt, and a lack of accountability. Problem: without architectural governance, organizations often grapple with inconsistent standards. Different departments or project teams make independent technology choices, leading to a sprawling, unmanageable IT landscape. Technical debt: quick fixes and short-sighted decisions accumulate, making future changes more expensive and riskier. Duplicated efforts: multiple teams independently build similar solutions because there's no central oversight or shared knowledge. Lack of strategic alignment: IT projects may deliver technically sound solutions but fail to support overarching business goals. Regulatory noncompliance: failure to adhere to industry-specific regulations, data privacy laws, or internal policies, leading to fines, reputational damage, and loss of trust. Importance: architectural governance provides the framework for effective decision-making, ensuring that every strategic architectural choice aligns with business objectives, leverages existing assets where appropriate, balances innovation with stability, and adheres to necessary controls. It's about finding the sweet spot between centralized control and decentralized execution, enabling agile development within a structured framework. Let's explore some key patterns that address these governance and compliance challenges. 7.2 Reference Architecture, the guiding blueprint. For organizations seeking consistency across projects and domains, a reference architecture serves as a powerful guiding blueprint. Problem: every new project tends to reinvent the wheel, selecting technologies and designing solutions from scratch. This leads to inconsistencies, missed opportunities for reuse, and a slower pace of development, often creating a fragmented architectural landscape. Solution: a reference architecture is a generalized, abstract, and canonical blueprint that defines the structure, components, and principles for a specific domain or across the entire enterprise. It outlines the ideal state of an architecture, recommending best practices, standard technologies, and preferred patterns for common functions. It's not a concrete solution to be directly implemented, but provides a template or a set of guidelines that individual projects or systems can then tailor. Benefits: accelerates development, provides a starting point for new projects, reducing design and decision-making time. Ensures consistency, promotes the use of standard technologies, design patterns, and integration methods across the enterprise. Reduces risk, guides teams toward proven solutions, minimizing experimentation with unsupported technologies. Facilitates reuse, highlights common components and services that can be reused across projects, reducing duplication. Improves communication, provides a shared understanding and common vocabulary for architects and development teams. Analogy: think of a corporate-style guide for branding. It doesn't tell a designer exactly what to create, but it provides standard fonts, color palettes, logo usage rules, and tone of voice. This ensures consistency across all marketing materials, regardless of who created them. A reference architecture similarly guides software and system development. For example, an organization might create a cloud data analytics reference architecture that prescribes the use of specific cloud services, e.g., a particular data lake solution, a chosen data warehouse service, a specific buy tool, integration patterns, e.g., event-driven pipelines, and security controls for all new data analytics projects in the cloud. 7.3 Architecture Review Board (ARB), Quality and Alignment Gatekeepers. To ensure that architectural decisions align with the enterprise's strategic direction and adhere to established standards, many organizations implement an Architecture Review Board (ARB) pattern. Problem: project teams, in their urgency to deliver, might make isolated architectural decisions that lead to technical debt, introduce security vulnerabilities, or fail to align with the broader enterprise strategy. Without central oversight, the architectural landscape can become fragmented and difficult to manage. Solution: an ARB is a formal committee, typically composed of senior architects, technical leads, and sometimes business stakeholders, responsible for reviewing and approving significant architectural designs and decisions within the organization. Their role is to ensure alignment, verify that proposed architectures support business objectives and enterprise strategy, Promote standards. Check adherence to established architectural principles, patterns, and technology standards. Identify risks. Proactively uncover design flaws, security risks, or potential integration challenges. Foster reuse. Identify opportunities for leveraging existing assets or common services. Guide development. Provide constructive feedback and guidance to project teams. Benefits. Improved architectural quality. Ensures designs are sound, scalable, and secure. Reduced technical debt. Catches and prevents suboptimal architectural choices early. Enhanced strategic alignment. Guarantees IT investments directly support business goals. Consistency across the enterprise. Promotes uniformity in design and technology choices. Example: a project proposing a new customer portal would present its technical architecture to the ARB. The ARB would review it for compliance with security patterns, e.g., IAM security zones, integration patterns, e.g., API gateway for backend services, data architecture patterns, e.g., MDM for customer data, and alignment with the overall business capabilities map. While ARBs provide essential governance, it's crucial to balance their oversight with the need for speed and agility, ensuring they don't become a bureaucratic bottleneck. 7.4 Center of Excellence, COE/Competency Center. Fostering expertise. To drive specific architectural initiatives, foster continuous learning, and ensure consistent application of new technologies or methodologies, the Center of Excellence, COE, or Competency Center is a valuable pattern. Problem: knowledge and expertise often reside in silos, leading to inconsistent application of new technologies, duplicated efforts in learning, and a lack of a unified approach to complex domains, e.g., cloud security, data science, agile development. Solution: a COE is a dedicated team or a virtual group of experts focused on a particular area, e.g., Cloud COE, Data Governance COE, DevOps COE, Enterprise Architecture COE. Its primary responsibilities include establishing best practices, defining guidelines, standards, and preferred architectural patterns for their domain. Knowledge sharing, acting as internal consultants, providing training, and disseminating lessons learned. Tooling and enablement, recommending and supporting the adoption of tools relevant to their area. Innovation and research, staying abreast of new technologies and trends and piloting new approaches. Mentorship, guiding and mentoring practitioners across the organization. Benefits, drives innovation, acts as a catalyst for adopting new technologies and methodologies effectively. Propagates best practices, ensures consistent and high-quality implementation across various projects. Builds internal capabilities. Elevates the skills and knowledge base of the organization, reduces risk, provides expertise to avoid common pitfalls in specific technical or architectural domains. Analogy: imagine a company that wants to standardize its use of artificial intelligence. A dedicated AI COE would research the best AI platforms, develop reusable machine learning models, train internal teams on AI best practices, and consult on new AI-driven projects, ensuring that the company's AI efforts are coherent and effective. 7.5 Policy as Code, automating compliance. In the fast-moving world of cloud-native and DevOps environments, manual policy enforcement struggles to keep pace. Policy as Code offers a solution by automating governance and compliance checks. Problem: compliance and security policies are often written as human-readable documents, making their enforcement a manual, error-prone, and time-consuming process. In dynamic cloud environments, resources can be provisioned and deprovisioned rapidly, making it difficult to ensure continuous compliance. Solution: Policy as Code involves defining security, operational, and compliance policies in machine-readable code. These policies can then be automatically tested, deployed, and enforced throughout the software delivery pipeline and across cloud infrastructure. Common tools include Open Policy Agent OPA, CloudFormation Guard, or Sentinel by HashiCorp. These tools allow organizations to define policies, express rules like all S3 buckets must be encrypted, or no EC2 instances can be publicly accessible, automate enforcement, integrate policy checks into CI/CD pipelines to prevent non-compliant deployments or apply policies to continuously audit existing infrastructure. Version control. Manage policies like any other codebase using version control systems, e.g., Git for traceability and collaboration. Benefits. Consistency and reliability. Ensures policies are applied uniformly and without human error. Speed and agility. Automates compliance checks, integrating them seamlessly into rapid development cycles. Scalability. Policies can be applied automatically across vast and dynamic cloud infrastructures. Auditability. Provides a clear, version-controlled record of all policies and their enforcement. Shift-left security. Catches policy violations early in the development lifecycle, reducing cost and risk. Policy as code is a crucial pattern for achieving scalable and continuous compliance in modern, dynamic environments. These governance patterns are critical for balancing the need for agility and innovation with the imperative for control and stability. They ensure that an organization's architecture evolves in a disciplined manner, consistently aligning with strategic objectives and regulatory requirements. In the next chapter, we will look at how to build architectures that are designed for continuous evolution and scalability in response to constant change. Chapter 8, Evolutionary Architectures, Enabling Agility and Scalability. In the constantly shifting landscape of the digital age, market demands, technological advancements, and customer expectations evolve at an unprecedented pace. An enterprise architecture that's static or rigid, however well-designed initially, is doomed to obsolescence. The ability to continually adapt, scale, and integrate new capabilities is no longer a luxury, but a fundamental requirement for survival and growth. This chapter focuses on patterns that help enterprises build architectures that are inherently evolutionary, capable of change and growth without requiring disruptive overhauls. 8.1. The Agile Enterprise. Architecting for Change. Traditional architectural approaches often focused on delivering a finished product, a grand design that would endure for years. However, this mindset clashes with the reality of modern business. Problem. Static, monolithic, or rigid architectures struggle to keep pace with rapid market shifts. Business strategies pivot, new cloud services emerge, customer data needs grow exponentially, and unforeseen global events demand immediate adaptation. An architecture that anticipates a stable future will quickly become a roadblock to innovation. Importance. To thrive, organizations need architectures that are inherently agile, capable of quick iterative changes and deployments without breaking existing functionalities. Scalable, able to handle increasing loads and volumes of data or users efficiently, both up and down. Resilient, designed to withstand failures and recover quickly without significant downtime. Composability, built from independent, combinable building blocks that can be rearranged or replaced. This shift in mindset from fixed to fluid necessitates architectural patterns that champion change and continuous evolution. 8.2 Capability-based architecture, unlocking business potential. Aligning architectural components directly with core business functions offers a powerful way to achieve organizational agility and clarity. This is the essence of capability-based architecture. Problem. Organizations often organize their IT systems around departmental structures, e.g., sales system, marketing application, or technical components. This can lead to fragmented, siloed solutions that don't reflect how the business actually delivers value. For instance, a customer onboarding process might involve systems from sales, legal, finance, and IT, making it hard to manage or improve end-to-end. Solution. Capability-based architecture designs and organizes the enterprise around distinct, self-contained business capabilities. A business capability is a particular ability or capacity that a business possesses or exchanges to achieve a specific purpose or outcome. Examples include order fulfillment, customer relationship management, product innovation, risk assessment, or employee onboarding. Each capability is defined by what it does, not how it does it or who does it. These capabilities are often mapped on a canvas, showing their hierarchy, relationships, and strategic importance. Benefits. Alignment with business strategy. directly links its investments to specific business outcomes, making priorities clearer. Reduces redundancy. By identifying core capabilities, organizations can avoid building the same functionality multiple times in different departments. Promotes modularity. Each capability can be supported by independent, modular IT systems or microservices, making it easier to change or replace components without affecting others. Facilitates evolution. When the business strategy changes, the impact on specific capabilities can be easily identified, allowing for focused architectural adjustments. Analogy: think of a modern, modular home. Instead of a single, indivisible structure, it's built around distinct capability units like a living space module, a kitchen module, or a utility module. Each module performs a specific function and can be upgraded, replaced, or expanded independently, offering greater flexibility than a traditional monolithic house. By focusing on business capabilities, organizations can achieve a more cohesive and future-proof design, where technology directly supports the agility of the business. 8.3 Cloud migration patterns. Lifting and shifting, or reimagining. The move to cloud computing is a significant evolutionary step for many enterprises, and it comes with its own set of strategic architecture patterns. Problem: organizations with substantial on-premise IT infrastructure face high operational costs, limited scalability, and slow provisioning times. Moving to the cloud offers immense benefits, but a haphazard migration can lead to unforeseen costs, security risks, or suboptimal performance. Solution: the 6 R's of cloud migration provide a common set of strategic patterns for moving workloads. Rehost, lift and shift, moving applications and data to the cloud with minimal changes. It's fast but doesn't optimize for cloud benefits. E.g., moving a Windows Server VM directly to AWS EC2. Replatform, lift tinker shift, making minor changes to optimize for the cloud without altering core architecture. E.g., moving an application from on-premise Oracle DB to AWS RDS, a fully managed database service. Refactor, re-architect, reimagining how the application is architected and developed, often leveraging cloud-native services, e.g., microservices, serverless functions. This is the most complex, but offers the greatest long-term benefits in terms of scalability, agility, and cost optimization. E.g., decomposing a monolithic app into serverless functions and connecting them via an event bus. Repurchase, drop and shop, moving from a custom application to a SaaS solution, software as a service, e.g., replacing an on-premise CRM with Salesforce. Retain, deciding not to migrate certain applications to the cloud, often due to regulatory constraints, technical complexity, or insufficient business value from migration. Retire, decommissioning applications that are no longer needed, reducing complexity and saving costs. Benefits: scalability and elasticity, dynamically adjust resources based on demand. Cost optimization, shift from CapEx to OpEx, pay-as-you-go models. Agility, faster provisioning of resources, access to cutting-edge cloud services. Resilience and disaster recovery, leveraging cloud providers' robust infrastructure. Case study idea: a traditional media company, struggling with peak traffic during major sports events, decides to migrate its streaming platform to the cloud. They might initially rehost some components for speed, replatform their video transcoding engines to use cloud-native services, and refactor their user authentication system into a serverless microservice to handle massive concurrent logins more efficiently. Choosing the right migration pattern for each workload is a critical EA decision, balancing speed of migration with depth of transformation. 8.4 API-first design, building for interoperability. In an increasingly interconnected world, where systems need to talk to internal applications, partner ecosystems, and external customers, API-first design is a crucial evolutionary pattern. Problem: often, APIs are an afterthought created after an application is built, making them hard to use, inconsistent, or limited in functionality, because they merely reflect the underlying system's internal structure. This creates friction for integration, inhibits partnerships, and slows innovation. Solution: API-first design mandates that the API, application programming interface, is designed and defined before any code for the underlying application is written. The API is considered the primary interface of the service, sometimes even a product in itself. This means, focus on consumer needs. The API is designed from the perspective of external consumers, making it intuitive and easy to use. Contract-first development. The API contract, e.g., Open API Swagger specification, is established and agreed upon before implementation. Parallel development. Client and server-side development can proceed in parallel once the API contract is solid. Benefits. Promotes interoperability. Ensures that systems are inherently designed to communicate effectively with each other as well as with external parties. Encourages reusability. Well-designed APIs become reusable building blocks. Fosters innovation. Enables third parties and internal teams to build new applications and services on top of existing capabilities. Faster time to market. Reduces integration bottlenecks and allows development teams to work concurrently. Analogy. When designing electrical systems, an architect defines the type of outlets and wiring connections before choosing specific appliances. This ensures that whatever appliances are later chosen, they will plug in and work seamlessly. API first is similar. Designing the interface ensures future flexibility and compatibility. Companies like Stripe and Twilio, which are fundamentally API-first businesses, exemplify the power of this pattern in enabling developers and partners to build innovative solutions on their platforms. 8.5 Distributed Ledger Technology, DLT, blockchain patterns, as an EA consideration. While still emerging for broad enterprise adoption beyond specific use cases, distributed ledger technology, DLT, which includes blockchain, offers patterns for trust and transparency in multi-party interactions. Problem: centralized systems rely on a single entity to maintain a definitive record, which can be a point of failure, a target for attack, or a source of distrust in multi-party transactions, e.g., supply chains, consortiums. Proving provenance or ensuring data immutability is difficult. Solution: DLT provides a decentralized, immutable, and cryptographically secured ledger maintained across multiple participants. While not a silver bullet for all problems, specific patterns where DLT adds significant value are emerging as EA considerations. Provenance and traceability. Ensuring transparency and verifiability in supply chains, e.g., tracking goods from origin to consumer. Digital identity management. Decentralized identity solutions where individuals control their own data and grant access. Multi-party shared records. Creating a trustable, shared data layer for consortiums or networks where no single entity is trusted, e.g., interbank settlement. Smart contracts. Self-executing agreements whose terms are directly written into code, automating trusted processes. Context. For EA, DLT isn't about replacing traditional databases wholesale, but identifying specific pain points where decentralization, immutability, and enhanced trust are critical. An EA pattern would define when and where a blockchain solution is appropriate, considering its trade-offs in scalability, transaction speed, and complexity. These evolutionary architectural patterns highlight the shift from static, fixed designs to flexible, adaptive ones. They are vital for navigating an unpredictable future, enabling organizations to continuously evolve their capabilities, processes, and systems to remain competitive and innovative. Next, we turn our attention to the often overlooked but crucial human element in enterprise architecture. Chapter 9: The Human Element, Organizational and People Patterns. Throughout our exploration of enterprise architecture, we've discussed blueprints, systems, data, and security. It's easy to fall into the trap of viewing EA as a purely technical discipline, focusing solely on the structural integrity of an organization's IT landscape. However, an enterprise is fundamentally a human endeavor. It's made up of people, teams, cultures, and communication channels. Ignoring this human element in architectural design is a critical mistake, as organizational structures profoundly influence technological outcomes and vice versa. This chapter delves into patterns that address the interplay between an organization's social structure and its technical architecture. recognizing that EA is only truly effective when it embraces the human factor. 9.1 Conway's Law in Action. Your org chart is your architecture. One of the most profound and often cited observations regarding the relationship between people and technology is Conway's Law. Problem: organizations often struggle with siloed systems, complex integrations, and inefficient communication flows between different applications. This is frequently attributed to technical challenges, but the root cause may lie elsewhere. Solution: Conway's Law's Insight. Proposed by Melvin Conway in 1968, Conway's Law states, organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. In simpler terms, the architecture of a system will mirror the communication structure of the team or teams that built it. If an organization has separate teams for sales, marketing, and customer support, they are likely to develop separate, loosely integrated, or even conflicting systems for each function. Implications for EA. This isn't just an observation, it's a powerful architectural principle. If an organization wants a cohesive, integrated set of systems, e.g., a microservices architecture where each service aligns with a specific business capability, then it often needs to structure its teams and communication channels to reflect that desired outcome. Trying to build a highly integrated system with highly siloed teams is an uphill battle. Case study idea: Global Widgets Inc., from Chapter 1, initially had separate teams for sales, manufacturing, and finance, each with their own applications and databases. This organizational structure directly led to their fragmented, spaghetti integration systems. When they decided to move towards a more integrated, customer-centric architecture, they reshaped their teams into cross-functional, value stream teams focused on end-to-end processes like order-to-cash. This organizational redesign was key to enabling the necessary architectural changes and implementing patterns like SOA and EDA. Understanding and actively working with Conway's Law is a critical EA pattern. It means that effective enterprise architecture often involves organizational design as much as, or even more than, technical design. 9.2 Communities of Practice, CoPS/architecture guilds. Spreading knowledge. In large, distributed organizations, ensuring consistent architectural quality and continuous learning can be a challenge. The Communities of Practice, CoPS, or Architecture Guilds pattern addresses this problem. As organizations scale, knowledge can become siloed within individual project teams or departments. This leads to inconsistent application of architectural principles, duplicated efforts in solving similar problems, and a general lack of shared learning and collective excellence. New innovations or best practices struggle to propagate effectively. Solution: a CoP or architecture guild is a group of individuals who share a common concern or passion for a domain and come together regularly to deepen their knowledge and expertise in that area by interacting on an ongoing basis. In an EA context, this might be a cloud architecture guild, a security architecture CoP, or a data governance forum. These groups are typically voluntary and self-organizing around shared problems. They share knowledge, present case studies, discuss lessons learned, and share new techniques or tools. Develop best practices, collaborate on defining and refining architectural standards and guidelines. Provide support. Offer peer-to-peer mentoring and problem-solving assistance. Influence strategy. Provide input to formal architecture governance bodies like the ARB and leadership. Benefits: fosters shared understanding. Creates a common language and approach across diverse teams. Accelerates knowledge transfer. New insights and patterns spread organically throughout the organization. Drives innovation. Acts as a crucible for new ideas and cross-pollination of expertise. Builds capabilities. Elevates the overall skill level and architectural maturity of individuals. Increases engagement. Empowers practitioners and provides a sense of belonging. Analogy: think of an informal book club or hobby group where passionate individuals meet to discuss their shared interest, exchange tips, and learn from each other. Unlike a strictly top-down training program, CoPS foster organic, peer-driven growth. 9.3 Architecture storytelling. communicating the vision. The most brilliant architectural vision is useless if it cannot be effectively communicated and gain buy-in from various stakeholders, particularly non-technical ones. Architecture storytelling is a pattern for effective communication. Problem: architects often struggle to translate complex technical concepts and their strategic implications into language that resonates with business leaders, financial managers, or even other technical teams who aren't steeped in architectural jargon. This leads to misunderstandings, lack of support, and architectural recommendations being shelved. Solution: architecture storytelling involves crafting compelling narratives that connect technical architectural decisions to tangible business outcomes, customer value, or strategic objectives. It means using analogies, as we've done throughout this book, cities, buildings, orchestras, etc., relating complex technical ideas to familiar concepts. Focusing on why. Explaining the business problem being solved rather than just how it's solved technically. Highlighting benefits, clearly articulating the value proposition, e.g., faster time to market, reduced costs, improved security, enhanced customer experience. Visual communication, using simplified diagrams, journey maps, and visual metaphors instead of overly detailed technical schematics. Tailoring the message, adapting the depth and focus of the story to the audience's level of technical understanding and their interests. Benefits: builds stakeholder buy-in, gains support and resources for architectural initiatives, facilitates decision-making, helps non-technical leaders understand the implications of architectural choices, reduces misunderstandings, bridges the gap between technical and business perspectives, elicits feedback, encourages constructive dialogue, and identifies potential concerns early. Example: instead of telling a CEO, "We need to refactor our monolithic application into microservices using a Spring Cloud architecture and Kafka event streaming," an architect might say, "To accelerate our ability to launch new customer features from months to weeks, we need to break down our large application into smaller, independent building blocks. This will allow different teams to work simultaneously and deploy updates more frequently." Much like a car manufacturer can update individual components without redesigning the entire car. 9.4 Strategic alignment and stakeholder engagement patterns. Enterprise architecture is fundamentally about bridging the gap between business strategy and IT execution. This requires continuous strategic alignment and stakeholder engagement. Problem: EA initiatives can become ivory tower exercises if architects operate in isolation, removed from the day-to-day realities and evolving priorities of the business. Projects might be architecturally sound, but irrelevant to current business needs or lack the necessary sponsorship to succeed. Solution: this pattern emphasizes proactive, continuous engagement with business leaders and other key stakeholders throughout the EA lifecycle. It involves value stream mapping, collaborating with business lines to identify the sequence of activities that deliver customer value, highlighting where architectural interventions can optimize flow, reduce waste, or improve quality. Business capability mapping, working with business leaders to define and prioritize key business capabilities, ensuring IT investments are aligned. Joint strategy sessions, participating in business strategy planning to provide architectural input and understand future direction. Road mapping and portfolio planning, translating business strategy into an architectural roadmap, demonstrating how technology evolution supports strategic goals. Regular communication, establishing formal and informal channels for updates, feedback, and collaboration with all relevant stakeholders, ensuring transparency and managing expectations. Benefits: ensures EA relevance, guarantees that architectural efforts are directly serving business objectives, secures funding and support, demonstrates the tangible value of EA to decision makers, manages expectations, provides clear communication about architectural scope, benefits, and timelines, fosters partnership, transforms the relationship between IT and business from transactional to strategic. The human element of enterprise architecture is not a fluffy add-on. It is foundational. By thoughtfully applying patterns that consider organizational structure, foster knowledge sharing, communicate effectively, and engage stakeholders strategically, architects can move beyond mere technical design to truly shape the operating model and culture of the enterprise for sustained success. In the next chapter, we will shift our focus to the practical application of all these patterns, charting a course for real-world implementation. Chapter 10, Applying the Blueprint, a practical guide to pattern adoption. We have embarked on a journey through the multifaceted world of enterprise architecture, exploring foundational concepts, diverse pattern categories, and the critical interplay between technology and the organizational human element. But understanding patterns theoretically is just the first step. The true power of these proven blueprints lies in their practical application, in translating abstract architectural principles into tangible, impactful solutions for real-world business challenges. This chapter provides a practical guide outlining a methodology for identifying, selecting, and implementing EA patterns within an organization, culminating in a comprehensive case study. 10.1 Beyond Knowing Patterns. Putting them to work. Imagine a master builder who has studied countless architectural styles, materials, and construction techniques. Their knowledge is immense, but without the ability to translate that knowledge into a coherent plan for a specific site, with specific client needs and constraints, it remains mere academic learning. The same applies to enterprise architecture. It's about more than recognizing a layered architecture or an API gateway when you see one. It's about knowing when, why, and how to apply them effectively to address an organization's unique context. The goal now is to bridge the gap between pattern recognition and intelligent pattern adoption. This requires a systematic approach, critical thinking, and the ability to adapt patterns rather than rigidly force them onto a situation. 10.2 The Pattern Adoption Cycle. Identify, select, adapt, implement, review. Applying EA patterns effectively isn't a one-off event. It's a continuous process of problem-solving and improvement. A useful way to conceptualize this is through a cyclical approach. Identify the problem opportunity. Action. Begin by clearly defining the business challenge or strategic objective. What specific pain points are organizations facing? E.g., slow time to market, inconsistent customer data, security vulnerabilities, difficulty scaling. What new capabilities are needed? This often involves engaging with business stakeholders, as discussed in Chapter 9. Tools: value stream mapping, business capability modeling, stakeholder interviews, current state analysis, e.g., system inventories, application rationalization. Outcome: a clear problem statement and desired future state. Select candidate patterns. Action: based on the identified problem, brainstorm and research relevant EA patterns. Consider patterns from different domains: strategic, integration, data, security, evolutionary, people, that could contribute to a solution. Don't be afraid to consider combinations of patterns. Tools: pattern catalogs like this book, architectural frameworks e.g. TOGAF, Zachman, industry best practices. Outcome: a short list of potential patterns that could apply. Adapt and design the solution. Action. This is where the artistry of architecture comes in. Patterns are templates, not rigid rules. Context matters. Evaluate each candidate pattern against the specific organizational context. Contextual fit. How well does the pattern address the unique constraints, budget, legacy systems, existing skill sets, regulatory environment? Trade-offs. What are the benefits and potential drawbacks, e.g., increased complexity, cost, performance implications of applying the pattern in this specific situation? Integration. How will this pattern integrate with the existing architectural landscape? Refinement. Tailor the chosen pattern to the specific needs. This might involve combining elements of multiple patterns or creating variations. Tools. Architectural modeling tools, e.g., Archi-Mate diagrams, decision matrices, proof-of-concept implementations. Outcome: a detailed architectural design incorporating the selected and adapted patterns. This design is what might be presented to an architecture review board, Chapter 7. Implement and build. Action: put the architectural design into practice. This involves development, configuration, testing, and deployment. Tools: software development toolchains, cloud infrastructure platforms, CI/CD pipelines. This stage often leverages organizational patterns like communities of practice, Chapter 9, for knowledge sharing and COEs, Chapter 7, for expertise. Outcome, a live operational system or solution. Review and evolve. Action, once implemented, continually monitor the solution's performance, security, and business impact. Gather feedback. Does it meet the original objectives? Are there unexpected issues or new opportunities? This feeds back into the first step, allowing for continuous improvement and adaptation. This is where evolutionary architecture principles, Chapter 8, are paramount. Tools. Monitoring systems, feedback loops, post-implementation reviews, technical debt assessments. Outcome. Lessons learned, necessary adjustments, and potentially new problems opportunities for future pattern adoption cycles. This cycle emphasizes that pattern adoption is an iterative and adaptive process, not a linear one. 10.3 Case Study, Transforming a Legacy Retailer. Let's illustrate this pattern adoption cycle with a practical example. Retail Co., a mid-sized, established apparel retailer facing declining market share due to slow online operations and fierce competition from agile e-commerce pure plays. Phase 1. Identify the problem opportunity. Problem: Retail Co. suffers from an aging, monolithic e-commerce platform integrated via point-to-point connections with various backend systems. Inventory, CRM, billing, loyalty. This causes slow feature delivery. New sales, promotions, or payment options take months to implement. Poor customer experience. Inconsistent product data, e.g., stock levels across channels, online Vs. In-store, slow website performance, difficult returns process. Data gaps, no unified view of customers across online purchases, in-store loyalty, and customer service interactions. High costs. Expensive to maintain the legacy system. Scaling for peak seasons is problematic. Opportunity. Reclaim market share, enhance customer loyalty, provide seamless omnichannel experience, reduce operational costs. Phase 2. Select candidate patterns. Given the problems, Retail Co.'s EA team considered several patterns. Strategic. Microservices architecture for agility in feature delivery, capability-based architecture to organize around product management, order fulfillment, customer engagement. Integration, API gateway for consistent external access, publish-subscribe for asynchronous communication between services. Data, master data management for unified customer and product data, data lake for analytics, future AI. Evolutionary, cloud migration from on-premise monolith, API-first design for new services. Governance, architecture review board to guide the transformation, center of excellence for cloud. Phase 3. Adapt and design the solution. Retail Co. designed a multi-phase transformation plan leveraging these patterns. Decomposition. Begin segmenting the monolith into microservices aligned with business capabilities, e.g., a product catalog service, an order service, a customer service. This was a refactor re-architect decision, cloud migration pattern. API layer. Implement an API gateway as the single entry point for all front-end applications, web, mobile, partner systems, to access the new microservices. API-first design was mandated for all new service development. Messaging. Introduce a publish-subscribe bus, e.g., Kafka, to enable asynchronous communication and strong decoupling between microservices, e.g., order-placed event triggering inventory update, payment, and shipping notifications. Data Hub. Implement a master data management, MDM, solution to create a single golden record for customer and product data, fed by existing legacy systems and new services. This MDM system would then be the authoritative source for all downstream systems. A data lake would capture all raw transactional data for future analytics and machine learning. Cloud adoption. Migrate new microservices and data platforms to a public cloud. Initially, rehosting some less critical legacy systems while strategically refactoring core customer-facing applications. Governance and people. Establish an architecture review board to guide the microservices decomposition and enforce architectural principles. Create a cloud and microservices COE to train existing teams and disseminate best practices. This also involved a strategic organizational redesign to align teams with new microservices, Conway's Law. Phase 4. Implement and build. Retail Co. executed the plan incrementally, often delivering small, valuable components first. For example, the product catalog service was designed and deployed first, followed by the order service, then redesigned the entire checkout flow. This iterative approach allowed for learning and adjustments along the way. Phase 5. Review and evolves. Regular reviews found that initial API gateway performance needed optimization under heavy load, leading to further architectural tweaks. The customer MDM solution showed immediate benefits in reducing data inconsistencies, leading to further investment. The process of decomposition was slow initially, but speeded up as the COE's impact grew and teams gained expertise. The entire journey was monitored against KPIs like time to market for new features, website performance metrics, and customer satisfaction scores. Outcomes: within 2 years, Retail Co. saw significant improvements. Agility: new features could be rolled out in weeks instead of months. Customer experience: consistent product information, faster website, and personalized offers due to the unified customer view. Cost reduction: optimized cloud spending and reduced maintenance burden on legacy systems. Scalability: the new architecture could effortlessly handle peak shopping seasons. This case study demonstrates how strategically applying a combination of patterns can drive significant business transformation. 10.4 Tools and techniques for pattern application. While patterns are conceptual, various tools and techniques facilitate their application. Architectural modeling tools. Tools like Archimate, UML, or even simple diagramming software, e.g., Miro, Visio, help visualize the current and target state architectures, communicate design decisions, and ensure consistency. Architectural decision records, ADRs. Short, focused documents that capture significant architectural decisions, their context, the options considered, and the rationale for the chosen pattern. This provides valuable documentation for future reference. Why was this done this way? Cloud architecture frameworks. Cloud providers offer their own architectural frameworks, e.g., AWS Well-Architected Framework, Azure Architecture Center, that embody many common EA patterns and provide guidance for cloud-native implementations. Road mapping and portfolio planning tools help visualize the phased adoption of new architectural patterns and connect them to strategic business initiatives. Communication and collaboration platforms, essential for knowledge sharing within communities of practice and for transparent discussions amongst the ARB and project teams. Applying enterprise architecture design patterns is a skill honed through practice. It requires a blend of technical expertise, business acumen, and a deep understanding of organizational dynamics. By following a structured adoption cycle and leveraging appropriate tools, architects can systematically transform their organizations. In our final chapters, we will address common pitfalls to avoid and look at the exciting future trends shaping the world of enterprise architecture. Chapter 11: Pitfalls and Progress. Navigating Challenges and Future Trends. We've now journeyed through the landscape of enterprise architecture, exploring how strategic patterns can provide blueprints for organizational coherence, integrate disparate systems, manage vital data, secure assets, and foster agile evolution. We've also seen how the human element is fundamental to successful architectural endeavors. However, the path to architectural excellence is rarely smooth. Organizations often encounter pitfalls that can derail even the most well-intentioned initiatives. Understanding these common anti-patterns is as crucial as knowing the patterns themselves. Furthermore, the digital frontier is constantly expanding, and anticipating future trends is vital for architects building systems that endure. 11.1 When good patterns go bad. Common pitfalls. Even the most powerful patterns can be misapplied or undermined, leading to outcomes worse than traditional approaches. Recognizing these traps is the first step to avoiding them. Golden Hammer Syndrome. Problem: an organization or an architect finds a new, exciting pattern, e.g., microservices, event-driven architecture, AI, that has a lot of buzz and promises. They then try to apply this single pattern to every problem, regardless of context or suitability. Consequence: forcing a complex pattern onto simple problems can lead to over-engineering, increased complexity, higher costs, and slower development cycles. Not every nail needs a golden hammer, and sometimes a simple screwdriver is more effective. Lesson: patterns are tools in a toolkit. The skilled architect knows which tool to use for which job and when to use multiple tools in combination. Context always matters. Over-engineering analysis paralysis. Problem: architects become overly focused on designing a theoretically perfect, highly generalized, and future-proof architecture before any implementation begins. This leads to endless documentation, theoretical debates, and little to no tangible delivery. Consequence: projects stall, business value is delayed, and architects gain a reputation for being roadblocks rather than enablers. In a rapidly changing world, a perfect design today might be obsolete tomorrow. Lesson: embrace iterative and evolutionary architecture. Focus on delivering minimum viable architectural components, gather feedback, and iterate. Good architecture emerges through continuous refinement, not exhaustive upfront design. Ignoring the human element, ivory tower architecture. Problem: architects design solutions in isolation, failing to engage with business stakeholders to understand their true needs or with development teams to understand practical implementation challenges. They decree architectural standards without collaboration. Consequence: beautiful architectural diagrams are produced, but development teams bypass them, business leaders don't see the value, and the architecture becomes irrelevant. Lack of buy-in and communication, as discussed in Chapter 9, spells doom for any architectural initiative. Lesson: architecture is a collaborative act. Effective architects are communicators, facilitators, and servant leaders. Their role is to enable, not dictate. Frankenstein architecture: lack of governance. Problem: projects and teams make independent technology choices and architectural decisions without any overarching vision, standards, or coordination, the opposite of the governance patterns in Chapter 7. Consequence: the enterprise accumulates a hodgepodge of incompatible systems, redundant capabilities, security vulnerabilities, and significant technical debt. The city becomes an unplanned sprawl. Lesson: while agility is important, some level of architectural governance, reference architectures, RBES, is essential to ensure coherence and avoid uncontrolled fragmentation. The key is finding the right balance, not too much, not too little. Big ball of mud, anti-pattern. Problem: a system that lacks a discernible architecture, where components are tightly coupled in arbitrary ways and there's no clear separation of concerns. It's often the result of continuous quick fixes, lack of documentation, and high developer turnover. Consequence: the system becomes incredibly complex, difficult to understand, nearly impossible to change without introducing new bugs, and very expensive to maintain. It stifles innovation and agility. Lesson: this is often the outcome of neglecting architectural patterns altogether. It emphasizes the need for continuous architectural oversight and refactoring to prevent decay. 11.2 The evolving landscape. Future trends in EA patterns. The future of enterprise architecture will be shaped by ongoing technological shifts, changing business models, and an increasing focus on responsible technology use. Architects must continuously learn and adapt. Here are some key trends to watch for: AI and machine learning in EA. Trend: artificial intelligence, AI, and machine learning, ML, are not just applications within the enterprise. They will increasingly become tools for the enterprise architect. Potential patterns: AI-assisted architectural discovery. Using AI to analyze existing systems, identify patterns, and detect architectural smells or anti-patterns in complex landscapes. Automated architectural decision support. Leveraging ML to recommend patterns or solutions based on context, constraints, and historical success rates. Predictive architecture. Using AI to forecast the impact of architectural changes or predict system behavior under various loads. Sustainability in architecture / green IT patterns. Trend: growing awareness of environmental impact, is leading to a focus on making it more energy efficient and sustainable. Potential patterns: carbon-aware workloads. Patterns for dynamically migrating computing workloads to data centers powered by renewable energy or during off-peak hours. Resource optimization. Architectural decisions that minimize energy consumption, e.g., optimizing code for efficiency, choosing energy-efficient hardware, leveraging serverless for idle periods. Hardware lifecycle management. Patterns for extending hardware life, efficient recycling, and responsible disposal. Composability/composable enterprise. Trend: moving beyond fixed architectures to highly modular enterprises where business capabilities are distinct, interchangeable, packaged business capabilities. PBCS that can be easily assembled and reassembled. Potential patterns: focus on designing APIs beyond just technical integration, data products, and business services so they are inherently discoverable, autonomous, and reusable, allowing businesses to create new solutions rapidly by combining existing capabilities. This is an evolution of SOA and microservices, explicitly driven by a business modularity perspective. Adaptive security/cyber resilience patterns. Trend: recognition that traditional security perimeters are obsolete, and organizations must assume breach and focus on rapid detection, response, and recovery. Potential patterns: automated threat response. Architecting systems that can automatically detect and respond to threats, e.g., isolating compromised systems. Chaos engineering for security. Proactively testing resilience to security failures. Security orchestration, automation, and response. SOAR. Patterns for integrating security tools and automating responses to security incidents. FinOps and cost-aware architecture. Trend: integrating financial accountability and cost management directly into architectural design and operations, especially in cloud environments. Potential patterns: cost optimization patterns. Decisions around right-sizing resources, leveraging spot instances, multi-cloud cost optimization. Unit cost accountability. Designing systems to easily track and attribute costs to specific business units or services. Automated cost governance. Policies as code patterns to prevent cost overruns and enforce budgets. Low-code, no-code platform integration. Trend: proliferation of graphical development platforms that enable business users or citizen developers to build applications with minimal or no coding. Potential patterns: architects need to define integration patterns, e.g., using APIs, governance models, and data strategies for incorporating these platforms into the enterprise landscape, balancing rapid ideation with control and scalability. While concepts like quantum computing, edge computing, and the metaverse also hold long-term architectural implications, the patterns described above are more immediately salient for most enterprises. The key takeaway is clear: enterprise architecture is not a static discipline. It requires continuous learning, curiosity, and a willingness to embrace change, not just in technology, but in organizational structures and ways of working. Understanding these common pitfalls and anticipating future trends will equip architects to build more resilient, innovative, and sustainable enterprises. In our final chapter, we will summarize the journey and offer a call to action for the aspiring and practicing enterprise architect. Chapter 12, Blueprint for Tomorrow, the continuous journey of enterprise architecture. We have journeyed through the intricate landscape of enterprise architecture, from its fundamental definitions to the nuanced application of various design patterns crucial for modern organizations. We've explored how seemingly disparate elements, business strategy, technology stacks, data flows, security protocols, and even human organizational structures are inextricably linked within the enterprise ecosystem. This final chapter serves as a recapitulation, reinforcing the transformative power of EA patterns, and offers a forward-looking perspective on the continuous evolution of the architect's role in shaping the enterprises of tomorrow. 12.1 Recapitulation: the power of proven blueprints. At its heart, enterprise architecture is about purposeful design. It's the strategic discipline that connects an organization's vision with its execution, ensuring that every investment, every system, and every process contributes to a coherent, resilient, and adaptive whole. The core message of this book is that enterprise architecture design patterns provide proven, reusable solutions for building scalable, resilient, and adaptable organizations. They are the accumulated wisdom of countless real-world successes and failures, offering battle-tested approaches to common challenges. We've seen how patterns manifest across various domains: strategic blueprints, patterns like layered architecture, SOA, EDA, and microservices help define the fundamental structure and communication paradigms of an enterprise, moving away from monolithic rigidity towards agile modularity. Integration imperative. Patterns such as message bus ESB, API gateway, and publish-subscribe unlock the flow of information across disparate systems, forming the digital circulatory system of the organization. Data as the new oil. Data warehouse, data lake, master data management, and data mesh patterns provide frameworks for capturing, storing, managing, and leveraging data as a strategic asset, turning raw information into actionable insight. Securing the fortress. IAM, security zones, principle of least privilege, and zero trust architecture are essential for baking security into the very fabric of the enterprise, protecting assets and ensuring trust. Governance and compliance. Reference architecture, architecture review boards, centers of excellence, and policy as code provide the necessary structure, oversight, and automation to balance agility with control and meet regulatory demands. Evolutionary architectures. Capability-based architecture, cloud migration patterns, API-first design, and even emerging DLT patterns emphasize that success lies in designing for continuous change, not just for a static endpoint. The human element. Conway's Law, communities of practice, architecture storytelling, and strategic alignment patterns underscore that ultimate architectural success hinges on understanding and influencing organizational dynamics, communication, and culture. These patterns are not rigid doctrines but adaptable templates. The skill lies not just in knowing them, but in intelligently selecting, combining, and tailoring them to the unique context of each organization, as demonstrated in our practical adoption cycle and case study. 12.2 EA as a living, breathing discipline. Perhaps the most crucial takeaway from our journey is that architecture, particularly enterprise architecture, is never done. It's a continuous, dynamic process. An organization's architecture is a living entity, constantly evolving in response to internal strategic shifts, external market pressures, new technological advancements, and emerging threats. This means that effective enterprise architecture requires continuous learning. The technology landscape is always changing. Architects must remain perpetual students, exploring new patterns, tools, and methodologies. Continuous feedback and monitoring. Systems must be continuously monitored for performance, security, and alignment with business goals. Feedback loops are essential for identifying areas for improvement or refactoring. Continuous adaptation. The architecture must be flexible enough to accommodate change without requiring wholesale replacement. This is the essence of building an evolutionary architecture, one that can be incrementally refined and extended. The architect, therefore, transitions from a designer of static blueprints to a sculptor of dynamic systems, constantly shaping, refining, and guiding the evolution of the enterprise. 12.3 Beyond the patterns. The architect's mindset. While mastery of design patterns is invaluable, it's the underlying mindset of the architect that truly sets the stage for success. This mindset transcends purely technical expertise, problem-solving acumen, the ability to dissect complex problems, identify root causes, and frame solutions holistically. Systemic thinking, understanding how seemingly independent components interact and influence the broader ecosystem. Strategic vision, translating business objectives into actionable architectural roadmaps. Communication mastery, the ability to articulate complex technical concepts simply and persuasively to diverse audiences, both technical and non-technical. This includes active listening to truly understand stakeholders' needs. Leadership and influence, guiding teams, fostering collaboration, and securing buy-in for architectural initiatives, often without direct authority. Pragmatism, balancing theoretical purity with practical constraints, understanding when to innovate and when to leverage established solutions. Resilience, navigating setbacks, managing technical debt, and continuously striving for improvement in a complex, often ambiguous environment. The enterprise architect is fundamentally a bridge builder between business and technology, strategy and execution, current state and desired future. 12.4 Your call to action, becoming an architectural leader. The insights and patterns shared in this book are not meant to be passively consumed. They are intended to be actively applied. No matter your current role, whether you are an aspiring architect, a seasoned technologist, a business leader, or a student of organizational design, you have the power to contribute to building better enterprises. Here are some suggested next steps. Start small, experiment often. Don't wait for a grand transformation project. Identify a single problem in your current context and apply one or two relevant patterns. Learn from the experience. Champion architectural excellence. Advocate for thoughtful design, challenge technical debt, and promote the value of a coherent architectural vision within your team and organization. Engage diverse stakeholders. Practice communicating architectural concepts to non-technical audiences. Seek to understand the business challenges that your architectural work can solve. Join communities of practice. Participate in architecture guilds, industry forums, or online communities to share knowledge, learn from peers, and stay abreast of new developments. Invest in continuous learning. Keep reading, attend conferences, explore new technologies, and reflect on past projects to extract architectural lessons. 12.5 Final thoughts. Building a legacy of resilience and innovation. The enterprises that will thrive in the coming decades will be those capable of continuous innovation and rapid adaptation. They will be organizations where technology is not just a cost center, but a strategic enabler, deeply intertwined with business capabilities. The blueprint for such organizations is not static. It is an evolutionary design, consistently shaped by conscious architectural choices. By embracing the discipline of enterprise architecture and mastering its powerful design patterns, you contribute not just to technical excellence, but to the very resilience, agility, and innovative spirit of an organization. You are not just building systems, you are building the future. May your blueprints be clear, your designs robust, and your impact profound.